Hi everyone, in this video I wanted to show you something different, this time with the plugin Karamba3d for Grasshopper. Let's see just a simple statical construction only in the plane XZ, and just parametrical lines of the system, different distances on how we can explore the deformations, or like here the moment diagram on y direction, and the utilization of the profiles when I apply the load here, like a point load, concentrated load. And let's go ahead to the video. Thank you for watching. So let's get started. I'm already in the empty Canva for this Karamba3d tutorial, and I have my extension Karamba3d. First, before I try to make the parametrical beam, let's just import the skeleton of this algorithm. What kind of components I'm gonna to need? So this is the assemble model. We are needing the element supports and cross-section and materials which are coming with the element itself, and then I'm gonna explain the joint and the supports. It's also very interesting, so let's go ahead. I want this model to be from beams, so I need the line to beam component, where also to create a single span beam I wanted to use the one fixed and one roller support. And the joints are also very difficult to create cross sections. I want to be able to select some profiles from this type, let's say. These are here all possible sections from the database, and with the item selector I can change it very easily. Item selector is from the human plugin. So cross section range selector, yes, I want the section selector, which I'm going to fit in the line to beam component. Yes, here I can take also the material. Material, there it is. Just looking for some material to select to be the fastest way. Okay, now we the settings for this. I need the load. This is some concentrated load like force going from the beam. I have as elements. Yes, this is not going to be all of the beams, but some indices. I can already assign the names. Let's just say this is A. Our IDs for the elements is going to be my elements. The load, for the load I need concentrated force in direction X with the value of 20 kilonewton, for example, and this is going to be the load. Now, in order to check if the model is not rigid system that is going to fall apart, I'm gonna need this component to analyze the model, and all of this is going to be displayed. Depends on what I want to see: reaction, supports, deformations, and section forces, which will be important. And if I know the displacement, beam displacement in direction X and Z, so in the plane. So this is pretty much our construct from Karamba side. Now let's assign the important lines and make them parametric. Let's go ahead. So now for the lines, I'm going to need the native Grasshopper components, and the model is combination of 4 lines that are going to be assigned in one list. Yes, and now this line components they need the start and end point. How I'm gonna to start? Am I start? So the first one is a point with coordinates. I just write the coordinates, and here is the beginning of my line. It's going to be some curve that is starting from 0 and goes to in direction x, some length of, let's say, 6 meter. I can change this. I can always change this. And now if I select it, I already can see it. So I want that the first part towards our hinge is changeable, and the second part of this single beam is also changeable. So in order to do this, I need the start and the end points of this unit, separate unit. And I'm gonna move the last point of this unit. Geometric, this is the end point. Again in direction x. For my second part, so here will be my support, and here in the 0 will be also my fixed support. Here I need some integer to be able to control this. This is the place, the second point where the hinge is going, and the the bending and the column, bending column is just above this point, but in direction z. So I need again the translation component to translate the geometry, but again this point, but in unit z, again with some slider for this one. Okay, and now let's connect the dots to our lines. So here there are first and second point. Let's say going here, one line, and the one point, and this going here. This geometry, yes, this is line, and for the last one, oh, here I wasn't right. Yes. So these are the beams. I can group this, make which one is my first support, the start line for my single beam. Okay, let's now take a look at the degree of freedom. In order to, first of all, make the stable construction around x-axis, we don't want to allow this movement, this rotation around x-axis. So therefore, by showing my cursor here, we see the word to be fixed. That means that selected means fixed. I'm fixing the rotation around x-axis, and also I'm fixing the translations through the 3 axes. Find all the supports in this component and feeding it in the assemble module. Second support will be my last point. So already the rotation on x-axis is fixed, and I need this to be roller, so that the translation on x is going to be free, and boom, stop only these translations to constrain them. I think is going to this component. Here I can check if the model is everything is good. So it's not a movable rigid system. Yes, here the view options are showing me already the reactions. Okay, let's for now we'll make the deformation 0. Sure. Let's see further. Oh, the joints also will be important because I want to make this system. So this is going to be so nice. Here is the hinge. It's going to experience only the pull force and find this one. Okay, so how I'm gonna do this? I'm looking at this component joint and I want to assign element. I want to assign it. Let's just turn on the elements. Tags element. Yes, now I see it properly. IDs, sorry, element IDs, not tags. Now I'm seeing the IDs which I gave. First joint is going to be on element A, so item selector. Vertical beam. And the second that we need is to geometry. I'm taking the point. This is the endpoints in this is the green one in this case, and I'm going to say to geometry. Now here the difference between beam joint, hinge, and the support is when I grab the cursor, here is saying to be fixed, and here otherwise is saying to be released. This means that here selection means released, and here selection means constrain. So this was interesting. And I want only to restrain not to restrain, sorry, to release my rotation around epsilon, around y axis in this plane. So in z. Okay, let's do this. Planes. We can collect them also in one joint component. Fit them in assemble model. Yes, I already see this release that and can show that this is there are no errors here. Now the second one, I need this to be on element like that at element B and to point here above to extract this point. So we need the element and the point just to geometry. And not only here, but this element needs also hinge here at the very beginning, because there it has to know how it is connected to this point, to this node. So here I'm going to need this first point. Here I'm releasing also the y direction. Yes, now I have the joints. And we are pretty much done with the settings and important methods. Let's see what happens here at the end, and let's play around. So deformation. Yes, I can check that the construction is not falling apart. That's very important. And in the end, I can show you how we can find the utilization of elements here and watch out the result in one panel. So for steel from type 235, we have some tension that is allowed after after the values that are multiplicated, after the values that are divided, we are getting the 21.8 kilonewton in centimeter per quadrat centimeter, per squared centimeter. And here we are seeing that value. I've already turned the utilization on, and of course I can make this value, I can change it and see how does it changed. How does it change? And yeah, feel free to try different things. And thank you for watching. Bye.